pin C. You see that there are roller here. So what does that mean? It means that we can imagine that it can move horizontally. Okay. And then it has pin here, which means it can. So it can rotate and it can move horizontally. Which means the reaction force that might come from this pin is only the vertical force. Do you get it? Right? So first, we can see the pin C is having the vertical force. And then if you compare with A is only having this rotation, which means the vertical and horizontal might happen. So it can be going there and maybe going there or going there. Okay? So we can write all those reaction forces. And we can write and simplify the bar structures just using the free body diagram. So we just draw the bar as just a thin line. Okay. So we can try to draw here. So it's going up a little bit, and then this will be about that much. And then this will be that. Okay. Now we name all the point A, B, C, D. And then give all the informations. This will be the distance 0.6. This will be 0.4. And then this will be another 0.6. And this will be it's 1.2. This will be 0.7. Okay, I think all the distance we have written. And then we write the reaction forces. So reaction force that is on C, we can write maybe going up like that, and we name CY. And then on the A, we can write down this is the AX, and then maybe just a slightly here, this is the AY. Okay. And then we have external loads that is on this D, or maybe on the same point here. This is 1 kilonewton. Actually, there is, I think, a typo. So the new edition, there is just a slight change the number. So this should be not 1 but 1.4. Sorry. I think this is for better calculations. So let me just change this to 1.4. And this 1.2 meter is going to be 1 meter. Okay. So this will be 1. Okay. So I think is that all? I think that is all. Okay. Now, the question is asking. The first question is reactions. So reaction at A and C. So first we have this as an extra load. So we are going to use directly sigma moment because we have distance. Okay, we have distance, we have extra loads. So either we can take this as a reference or this, and then we can get both of them. So first, to make it easy, because A has two different reaction force. So let's try this one as a reference so we can get this Cy. Okay? So let's take that. So, and it's already provided all the distance, so we can write the sigma moment with reference A, and this will be, that is the positive if you rotate that way. This is equal 0. So we are going to have the 1.4 multiply with 1 plus 0.6, right? Or let me write with the units. Okay. And then Cy is minus, so minus Cy multiplied with 0.6 meter equals 0. So Cy is basically 1.4 kilonewton multiplied with 1.6 meter divided by 0.6 meter. If you have a calculator, you can try to check. I think because it will divide by 3, it will be decimals with 3 at the behind. Let me calculate to make sure it's correct. Okay, 3.73. Okay. Since we have Cy, then we could directly get Ay with the sigma f. Okay, so let me write here that the sigma f y is 0. So Ay plus Cy is equal 1.4 kilonewton, or Ay is Ay is minus 2.33 kilonewton. So it should be going down, but let me just write that first. Okay. So we have Ay, we have Cy. Okay. Okay, any other things? I think Ay, Cy. And then since there are no other external loads that is on horizontal, we can say that the Ax is 0. Okay. So, or maybe to complete the answer, we can write the sigma f for x-axis is 0. Okay. All right, so we move on to the second question. The F1, F2, and F3, that all of them are on the member AB, BC, and CD, okay, which signifies from this number 1, 2, 3. So F1, F2, F3. Okay, now to get through that, then we need to make another simplified free body diagram. So we need to have our diagram having this 1, 2, and 3. So I think better just to take this bar, right? Because this bar, we can treat this as with the F1 here, F2, and F3, okay? So let's do that. So we can take that as our bar. Okay, so this will be A, C, and then this will be F1. This will be F2, and this will be the F3. Okay, now some important distance that need to be written here is this distance. This will be 0.4. This is 0.6. And then for the F1, since this is 0.6, same side, so we must have this angle is 45 degrees, right? Because we want to make sine and cosine components, okay? So we can write that here. This part here, let me just write, okay, this will be 45 degrees. Okay, and then we might have something here, which we can derive some angle from this distance here. So we can have a tangent. Tangent this over that, take inverse, and we get some angle for this one. So we need to use calculator, I think. It's not a special angle, so having maybe decimals. Okay, I think what else? Oh, we need to write down all the results, Cy and the Ay here. So we can write down. So Cy we have here, right? So let me just write this as 3.73. And then Ay is 2.3, but it is negative if we take upwards. So I will write downwards to make it positive. So we helping our computation here. So this will be Ay, which is 2.3 kilonewton. Now I think we have all, right? So first is to get the F1, we can take C as reference for the moment, right? So we can take this, and then we can take C as a moment. So this will be like that. But since there are two ways of working on something like this, because we are not in the really horizontal positions, we can think this bar, we need to make it that way with some angle that need to multiply. Or we could make this into two components, and then this one will use this distance to make the moment. Okay. So I think I will write F1 as a two component and making that as a C as reference. Okay. So we would like to make the sigma moment at C, which usually we take that as a positive. Okay, let's say that is the 0. And then we might have two components from F1. I think I will write with blue. This one here. And this one there. So this was F1 sine 45. This is F1 cosine 45. So, okay. So F1 sine 45, that is, I think, positive. It's going clockwise. F1 sine multiply with the 0.6 meter, right? And then plus F1 cosine 45, this is 0.4, right? And then what else? The Ay, the 2.3. 2.3, that is the, I think, minus. So minus 2.3 kilonewton multiply with 0.6 meter. Okay, so from here we should get F1, right? So this one, sine 45 and cosine 45 is the same, right? So I think it's safe to say we have this and this, which is 1, so we can ignore that. And this will be equal to 2.3 multiplied with 0.6. What is that? Let me just write here. This will be 4. Okay. And then this will be F1 is 5. More or less, that is F1. And I believe the answer key I have copied, the answer key is around this number. You can check if it's different, then you can use your own. I haven't checked whether this is correct, but I think still okay. The number still makes sense. Okay, now to provide the F2 and F3, since they are having two forces on one point, I think we might need, this is just my idea here, maybe we can take B here as a reference. So when we take B as a reference, we are going to have this vertical line as our distance, and we could make the F3 components. Okay? So F3 can be written as this and that, but we are going to use only this part, right? And the theta, as I mentioned, we can use from the tangent inverse. So it's not really a good number, so it has maybe decimals. So let me write here the theta. So theta is tangent inverse of what is that? 0.7 over 1. Can you check your calculator? Do you bring? Can you check? Is it correct? 35 or 36 or I haven't checked. What is tangent inverse of this? On the decimal, right? Okay, so I think we can just make 35. So this is okay. Like if you in exam, like you have some decimals, you want to make it a whole number, it's okay. So this will be around 35. Okay. So we take the moment. Let me make this a little bit smaller. So let's see how much time we do need to work on this. So let me write here this sigma moment on B. And again, this is the reference. This is equal 0. So here is the F3 cosine 35. Okay. This one is actually F3 sine 35. But because we take reference on B, the line or the forces that is parallel to this distance we can ignore. So we can focus that this will be our only force if we take this as a reference. So this will be that way. Oh, and we have the I forgot we still have the 2.3 that we can also take for B. So this will be, let me write here, f3 cosine 35. That will be a negative, right? Negative, then this will be 1 meter. And then we can have the AY using the 0.6. So AY will be 2.3. That is also minus, so minus 2.3 kilonewton, 0.6 meter equals 0. So f3 cosine 35 is equal negative 5.131. So f3. So divide cosine 35. It's around negative 1.71 kilonewton. And then we can get the F2 from the sigma F vertically equals 0. So 3 F1 so F2 plus F1 sine 45. Oh, I think I need to resize this to make it okay. Resize, go over there. Resize, move over there. Okay. And then plus the F3 sine 35. And then minus 2.3 plus 3.73 equals 0. Okay, so I think that's all the forces, right? We can compute this part, F1, F3, with the sign, each one of them, and put in the calculator, and we get the F2, okay? So F2 will be around negative 1.82 kilonewton. So this will be, negative will be mean compressive, this will be compressive, this will be tensile. But I think to get familiar with this, you could try many possibilities. Like you could try maybe sigma moment, not only C, maybe A, and sometimes you could see like what will you get from that equation, because sometimes when you work something like this, it's not always like you need to work like 1, 2, 3, 4 according to the order. Maybe you could work from the other way around. Somehow maybe it could be solvable as well. You can find a solution as well. But the most important thing is the very first step that you need to work on is to draw the diagram, okay? The free body diagram, and works and define all the forces that is possible in those diagrams. Okay, I will give you later the notes. I think we can, for the last, hopefully we have time. For the last one, there will be one more questions here, okay? I hope we can have enough time. Now, we have a distributed force, okay? So you see, the forces is different, the left and the right. It goes bigger when we move to the right, and then it's linearly bigger. Okay, so you could think this like a function, and then we can see another loads here, and then we have all the distance, and then this is a roller here, pin, and this is pin joint. So of course, if we could see all the pin, then we can define what is the resultant or what is the reactive forces. But before we continue to find the axial forces, the shear, and the moment at B, we could define this distributed force first. Okay? So if you remember, distributed force, if you have a distance, what does it mean, and how? If you see the units here, it's kilonewton per meter. So we could define this as a function of this distance, right? A function of x, or a function of this distance here. The whole distance here is 2.4 meter, right? So if you see this, we could think this like a geometrical shape, okay, in geometry. So if you could clearly see, to make it easy, I will draw a line here. So you could see two different shapes. It's a rectangle and the triangle. Okay. Now, if we multiply the distributed forces with the distance, we can get the force, right? Meter cancel. We get the force. So we can treat this like area of geometry. So we can treat the resultant force in area. So we can multiply finding the area of the rectangle. Okay? So this one is 1. Okay? This one is 2. But then, if this is the same as this is also 1, and this is also 1. Okay? 1, 1. So first, for the rectangle part, 1 multiplied with 2.4 is 2.4. So there will be 2.4 kilonewton resultant from this rectangle. And where is it? It should be in the middle. For the rectangle, it should be in the middle. Okay? I think that is statics, right? Or no? Have you learned that in statics? Oh, it's already evaporated, sir. I don't remember. But let me write here for you. So this will be 2.4 kilonewton. Okay, that is from the rectangle. And then we see the triangle. The triangle, the area is half base and height. The base is 2.4, the height is 1, so 2.4 divided by 2. It should be 1.2, right? But how we should write? Where? Anyone remember? Is it the same? Should be, yes. So remember, if you have a triangle, you will have three different proportions. You can imagine the triangle could be cut by 3. So this, maybe that, and 2.4 divided by 3 is 0.8, right? So you could see 0.8, 0.8, 0.8. You need to take, because it's bigger here, so it's going to be 2/3. So it should be 0.8 from the right. Okay, you get it? So I will make this as maybe around here. This is 1.2, and this will be 0.8 meter. Maybe let me write a little bit left to make it clear. Or maybe let me write clearly. This is okay. Now we have all the resultant from the distributed force, and then we need to. The first question is reactions at supports B. So we might as well to work this in another diagram if you want, but I think I will just use this one. I hope it's still clear. Okay, do I need to draw again? I think let me just draw again to make it clear. This is 1 kilonewton. And then this will be this will be 0.6. Zero point two, 0.2, and this will be 0.8 meter. So we should have here is the 1.2, and this is 2.4. Okay, and then what else? Oh, we have the point here is A, C, and then here is B. Okay. So B is a roller, so it horizontally can move freely, so it has only vertical. So let me write here is BY. And here is C. We have CY and CX. Okay, I think because we want to know B and C, we can find B first. That is supposed to be easy. So first is taking the moment. And let's say this is going to be positive there. Moment at C. Okay. So negative 1 kilonewton. This is 4 meter. And then plus BY 2.4 meter. And then plus minus 2.4 kilonewton. And then let me make it there. Another minus. This will be 0.8. Okay, so we get By. You could check the answer, but I will just write, I have copied the answer is 3.267 kilonewton. That is By. And then to get the Cy, we could just use the sigma force. So -1 kilonewton plus 3.267 By, and then minus 2.4 minus 1.2 and then plus Cy. And then from this calculation we get Cy is around 1.333 kilonewton. And I think there are no other horizontal force, so Cx is 0. I think this can be resized a little bit small. This also can resize to get a smaller. Okay. Now what else? The question is the internal resultant at D. Okay. So FD, VD, and MD. So the internal resultant, we are going to cut D over. Okay, cut here. So when that happens, we can actually imagine, let me use different color. Let's make this line as a reference. So the distance is only now at 2.8, right? So write the same here is the 1 kilonewton. And we have another different distribution force because we cut here. So we might have this shape here, okay? So different rectangle and triangle, different area. Okay. Okay. So this is 1 kilonewton per meter. And then how do we know this? Let me tell you something here. This is also one tips for you. This is if this is x. To get this x, how much we have? We can get from the triangle ratio. Okay. So we have triangle ratio from here, right? So I think we can make that. Because sometimes it's not in this course, if you look at the textbook, they didn't tell you how to get this. So I will give you some tricks to get the answer. So this is 1. Okay. This is, let's say, 1.2. This is 1.2, right? So we have x here. So x over 1.2 is equal 1.2.4, which means x is 0.5, okay? So this x is 0, or let me just write here that this is could be 0.5 kilonewton per meter. So within this new shape, then we get the new resultant force. Okay. So 1 is another rectangle, which is 1.2. So this will be 1.2 kilonewton. And for the rectangle, is 0.5. We'll go with this. It will be 0.6, but divided by 2, so 0.3. 0.3, since we have 1.2, it should be 0.4 from the right. So let me write here, maybe around here. Okay, so I think we get all, and then still the same, we get the B here, right? This is BY. And what else? I think all the resultant done, and we need to write at D, we should have the axial forces, the internal axial force, or the normal force here, FD, and then the shear force, and the moment. And then the same, we are going to write all the possible forces, make it 0. And I think we could done the horizontal first, because there is only one forces, FD, and there's no other forces, so FD, so the normal forces is 0. And for the vertical force, since we get By before, then we could write -1 kilonewton plus 3.267, and then minus 1.2 kilonewton minus 0.3 kilonewton, and then minus Vd. So we get Vd is around 0.7667. You can check again using your calculator. I haven't really checked all the answer. And then sigma moment. Sigma moment at D, okay, the reference. And let's say this is going to be positive over there. This is equal 0. So -1 kilonewton. So this will be, the total is 2.8. So 2.8 meter. And then plus 3.267 kilonewton. Multiply with 1.2 meter. And then what else? Minus 1.2 kilonewton, 0.6 meter, minus 0.3 kilonewton, 0.4 meter, and lastly, the moment at D, which is minus md equals 0. If you check, the moment is going to be around 0.28. Since it's positive, then it should be going to be or maybe negative. Maybe negative. Sorry. Maybe this is negative. Negative, right? Yeah, it should be negative. So